So in today's lecture, we're going to begin with a quick review, and then we're going to move on to looking at what actually happens to rocks themselves when we bury them. So last lecture, we looked at what happens to the organic components, how they transform from plankton through towards broken down molecules to kerogen, and finally, ultimately, to useful fluid hydrocarbons, ultimately ending up at natural gas before making a pathway potentially to graphite, which is not useful to us. So the goal today is going to be talking about rocks themselves and the processes that are involved when we bury rocks and then when we alter them, right, to take that sediment and turn it into a sedimentary rock, which is a term that we're going to refer to as diagenesis. Remember that petroleum guys use diagenesis to refer to transformation at relatively low temperatures of oil and gas. Geologists specifically reserve this term diagenesis for the totality of changes that occur to sediment on its pathway towards being a sedimentary rock. So includes a much larger suite of changes and also includes temperature. So that is how much higher temperature. So that's how I'm going to be using diagenesis. All right, so a quick review. Remember that we were talking last time about how the oil gets out. So this primary migration, this is where we are producing our hydrocarbons in the rock and they are moving out of the shale, right? And when they move out of the shale, they're going to migrate through what we call the country rock, which is just the surrounding rock, ultimately, hopefully on the way to a reservoir somewhere, but potentially all the ways out to the surface where they are no longer useful. And we looked at the various processes that are involved in each, and we reviewed that this secondary migration, this pathway towards the reservoir, as it flows through the rocks, right, this is going to be a density-driven buoyancy kind of movement. But this is what I want to talk about, and why I'm talking about the changes to the rock, is because as it moves through, right, as you are, you're on a pathway, you are moving through a rock, right? Depending on what you are moving through, that pathway can either be inhibited, right? You can have something that effectively acts as a barrier or seal, or it can be something that allows a pathway through. Right? Ultimately, when you get to something, when you get to your reservoir, to be an effective reservoir, you need to have certain properties that we'll review in a second. And so that's why we are going to review what happens to rocks, because all of the changes when we bury a rock are what are ultimately going to result in a rock which is capable of either transmitting or storing hydrocarbons. Okay, so let's continue on. Let me get rid of this guy here. All right, so a quick review of terminology. I'm going to remind you guys when it comes to the actual like fluid mechanics of moving this stuff through, especially on a mathematical level, honestly, you guys are in a better position as engineers. This is your forte. I'm more interested as a geologist in the environments of formation and how different materials are deposited and change in terms of compaction and geochemistry as you move it down. But the actual fluid flow stuff, this is going to be pretty elementary. But just in case you have not gone through this, let's remind that the two principal characteristics when we're talking about a reservoir or country rock, that is the rock that the material may flow through on its journey as it goes to a reservoir, are first porosity, which is just a measurement of the total volume which could store hydrocarbons. So this could be the total volume which is actually empty, or it could be volume which is occupied, but it's the stuff that is not rock. So in this case, all of this material here is pore space. That is its porosity. And we just measure this in terms of a relative amount, so percentage of the total. If this had 50% porosity, half of this box would be occupied by white space, and that could be occupied by oil and gas or water, and the other half is going to be occupied by rocks. Permeability, on the other hand, is the degree of connectedness of any given pore. So is this pore space here and this pore space here, are they connected together? That is, can that oil or gas flow down here or vice versa? If they're not, right, if these guys are separated by a barrier, by more rock, right? This could be porous, but it is not permeable. They're interrelated, but they are not the same. They are not the same idea at all. They're both super, though, important when we talk about country rock or when we talk about a reservoir. So here is a quick quiz for it. Think about this. If you already know the answer, well, then shh, don't tell your imaginary peer. I guess that doesn't work if we're not in the classroom. So take a look at these. These are two rocks. two hypothetical rocks, and they are, of different grain sizes. So you imagine these things are pebble size. Let's say they're just the size they are, and these things here are smaller. Or these could be microscope images, and these might be, large grains of sand, and these might be small grains of sand. So the question is, in these two cases, which one of these two things is going to have greater porosity? That's a big question. And the answer, surprisingly, is not what you might think. It looks like, oh, you see big spaces over here. There's big spaces over here. But remember, there aren't very many of them, right? So you've got obviously large spaces, but not very many. On the other hand, over here, you've got tons and tons and tons of little spaces. And so when you look at these things, somewhat surprisingly, the total amount, if you assume that the shape of the grains is the same in both cases, right? So the shape of the grains is the same in both cases. These guys are going to be, let me get my little thing over here. These guys are going to be equal, right? The shape of the grain is going to be the same, and the arrangement of them relative to each other, those are both equal. If you imagine those are both equal, then surprisingly, these guys are both going to actually have the same relative amount of porosity. So despite the fact that, these are much larger things, and each space is larger, because there are more of these small spaces, they actually have equivalent porosity. So that's a bit counterintuitive, but I think you can see that that is obviously the case, and there's some math there if you want some math. So that is a quick reminder there. So let's talk now about types of pores. So here is some terminology. This is going to be at least on a multiple choice test, so make sure you know this. So we've got three types of potential pores here. Quaternary pores, cul-de-sac pores. They have some different names sometimes. I forget what the other name is. I've seen it in writing, but cul-de-sac pore is what we're going to use here. And then a closed pore. So a quaternary pore is one where there is more than one opening, and that means that any fluid is capable of flowing through here. It also means that I can put pressure on this end. I can put a pressurized fluid here, and I can drive out whatever this material is. I can force it out there. Right? So I'm capable of flushing out this pore here. This one, on the other hand, I'm not capable of flushing out. Now, that doesn't mean that this material here, if this is full of hydrocarbons in here, it does not mean that material cannot be extracted. Remember that if I change the pressure over here, if I change the pressure over here and I cause this material to expand in volume, then it's going to no longer fill this area up, and some of it is naturally going to come out. So some of this material, although not all of this material, can be extracted. And if I start pumping out this reservoir, if I start removing material from this, right, start actually pumping out material, right, some of the hydrocarbons, some of this is just going to naturally migrate out. On the other hand, I can actually flush this thing out. So the recovery in this type of pore is obviously going to be greater than the recovery in this type of pore. This guy over here, until recently, was useless to us. We couldn't do anything at all with this. Now, of course, we can hydraulically frack, and that means that suddenly this pore, which had no outlet, it could not release its hydrocarbons at all. Now this guy, we can frack, we can make cracks. It's now capable of moving out through those cracks. And so these are the guys, these closed pores, that are now accessible through non-conventional technologies. Okay, so there is a quick bit of terminology and a reminder of that. So that means that when we are looking at calculating porosity, it's not simply just a matter of figuring out what the porosity is. That's interesting. What we're interested in, though, from a petroleum quantification sense, is what is the effective porosity. That is, what is the porosity that is actually connected? What is the porosity that also has permeability? Because unless we frack it, this is useless to us. So if we include that in our calculation, right, that is going to be misleading us. We're interested in this pore space, because this is the pore space which is capable of migration, or this pore space right here, right? So this might only have, well, this actually has two ways out. None of these are cul-de-sac pores here. This says it's a cul-de-sac pore, but it's got two ends. You really could flush that out. I don't know why they made that in the drawing. Let's just fix it. Let's put here, I'm going to connect that. Now it's a cul-de-sac pore. There we go. It's a bad drawing. Okay, now it is a cul-de-sac pore, so we can't flush it, but we could, still capture some material through it by changing the pressure. Okay, let's get rid of all of our stuff here. So remember this. This is what we were talking about. If I asked you a question that said, like, how is effective porosity different from porosity? Porosity, remember, is a calculation of the total percentage of it which is not occupied by rocky material, whereas effective porosity is a combination of your quaternary or your interconnected and your cul-de-sac pores. Now, do remember, though, that these guys are going to yield more than these guys, these dead end or cul-de-sac pores. So really, it's still, if you look at this just in pure numbers, you don't break this down, this is also a slightly misleading calculation in terms of trying to estimate actual recoverable volume of oil or gas. Okay, so here is a diagram. Just again, I'm going to beat this horse. We're not actually going to cover a lot of topics today. But the ones I do have, I really want to make sure you understand. So here's the first one, right? So here is no porosity, no permeability. You need to have permeability is a measure of the connectedness of pore space. So by definition, if you have no porosity, you don't have any permeability. On the other hand, here you've got lots of, let's get rid of that. That's not good. Here you've got lots of pore space, but those pore pores are entirely isolated, and therefore you have zero permeability in this example. And here you have some combination, that one is isolated, but these other ones over here, this space here is capable of flowing out like this, and it's also capable of being flushed out, right? So this one here has lots of effective porosity. All right, so let's move on to another idea, and this is this idea, it's a related idea to permeability. So this is the idea of wettability, and it's possible that in your other classes you might get into more of the chemistry of this and exactly how you measure it. I'm not super concerned about that. I'm concerned that you understand the basic idea. And the basic idea is just this, is that some materials attract water preferentially, some materials attract oil preferentially, and some of them in mixed materials are going to attract water in some areas and oil in some areas. So given that most of the times the fluid mixture we're looking at is multi-phase, we've got various things, we've got oil and gas and water all mixed together, how it will actually behave as it moves through, or as it settles within a porous material, is going to be dependent both on what the actual mixture of oil and water is, but also on what the preference of the rock material is itself in terms of what is attracted to it. So here is an example of a water-wet rock, and in general, these tend to be these are generalities, but in general, clastics tend to have, and mineralogy is going to make a difference, but in general, clastic things like sandstone tend to be water wet, and limestones tend to be oil wet. That's a generalization. So in this case, you can see that the water, let me get my blue here for water. Here's the water. The water is attracting itself. It's coating the edges of the grains. It's coating everywhere it can touch. It's coating the edges of the grains. So that means, here, right here, you could not, this spot here, that is not a pathway to oil. You could not get through there, right? That's not a pathway you could have gone through, but let's say, actually all of these are pretty much closed off. Let's just pretend that, let's find one I'll pretend over here. Let's pretend that this is water right here. I'm going to make that. So that's how it was. So if that is the case, then ordinarily oil would have been able to flow, if that bit of oil would be able to flow straight through and get over here. Except that it can't, because this passageway is being entirely blocked by water. Which means that even though, in theory, in my modified diagram here, there actually is permeability, in function, right, this permeability doesn't exist. Because that water, which is clinging to this grain and clinging to this grain here, are actually blocking entirely that space. So the only way you could squish oil through here is if eventually you built up enough pressure of oil that it kind of forced its way through, and then it created not just a little blob of oil stuck in the middle with water on either side, but actually a continuous sequence of oil. Right? So you get a continuous sequence of oil, then it would flow through there. So when oil is flowing, generally speaking, in reservoirs, it's not actually flowing drop by drop by drop. Most of the time, you have to build up enough pressure that it actually forces its way through and creates a continuous stream, right, that moves up towards the surface. Okay, so let's get rid of this, and I'm going to move on to the next slide. Let's move over here. Oh, let me just go back here and I'll look at this. So this is effective permeability. Effective permeability. So effective permeability is just a reminder that in practice, right, the theoretical permeability, the degree of interconnectedness of rocks, right, of pore spaces, is actually limited by the fact that they're often blocked and filled by fluids that will stop or impede, right, the passage of the things that we are interested in moving. Okay, what is next? Next up is a diagram just showing you the same thing in the basic idea. And this, by the way, is one of the ways we measure it. So they measure it both by putting, putting oil or water on the surface and watching how quickly it goes through. They do things where they force it through and see what comes out. But one of the simpler ways they do it is they actually do, under a microscope slide, they take a sample of the rock, they surround water by oil, and they just measure the angle that's formed at the interface right here. Right, so this is an example of water wet. So the water is, it's holding right on here. It's just going, it's spreading itself over. And so the angle of that junction, this junction right here, is going to be less than 90 degrees. Whereas over here, this thing is forming a nice round droplet, right? And it's obviously a bigger droplet like this. And so this angle is going to be greater than 90 degrees. So this is one of the ways that these numbers, whether you're oil wet or water wet, one of the ways they're quantified is actually just by measuring the angle formed when you put a single droplet in an experimental setting. And here is an example showing where here's your water, it's caught here, and here, I should be able to flow straight through here, but I can't because I've got this water here, and here's my little droplet of oil, and it's stuck. Right, that little droplet of oil can't go anywhere. Right, the only way that's going to get anywhere is if enough pressure builds up here that this moves up, connects to here, and then that forces itself. This is blocked, but I mean, imagine that wasn't blocked and it could come through there. Right. So again, this little droplet is not going to migrate. Often you see diagrams where it's single little droplets migrating through these systems. They don't really move through as little droplets. Generally, they move through as connected streams that are moving through. That's the only way they can in a mixed system like this. Okay. What is next? Next up is the same diagram, more or less, but reminding you that even if it's not totally blocked, so let's look at this example right here. Here is my example where it's actually blocked here. Here it's not totally blocked, but if you were to measure, you're trying to measure what the permeability is, right? You could say, okay, well, the grains are this big, and so the diameter is that width, right? That's the diameter. Except that's not really the diameter because this water's on the edge. The actual width of this area that it's able to flow through is this. It's a tiny fraction. I mean, that's about a third of what you would calculate if you just knew what the porosity was, right? Or just measured, on average, the permeability here, right? The functional permeability is much, much lower because the water is getting in the way there. And so this is why we need to talk about effective permeability. So again, expect if I had a question that said, geologists and engineers often refer to the effective permeability of a rock. What do they mean by effective permeability? You'd have to say, well, the actual permeability of a system is limited by the fact that where you have mixed fluids, sometimes the fluids are attracted to the grains and therefore, inhibit, they narrow the actual passageway, right? The radius of the pore throat here, if you want the proper terminology, right? The radius of the pore throat is being limited, and that for the actual effective permeability, that is what actually occurs in practice, is lower than what should be theoretical, just based on a evaluation of the rock itself. That once we add that second fluid stage in here, that is going to reduce the actual functional or effective permeability. All right, let me get rid of my stuff and we'll move on to the next slide. Okay, so now what? So that is a discussion of how material is flowing through or residing within a reservoir or country rock. But I want to talk about how do you actually get these rocks with these various characteristics. And we're going to start by looking at variations in rock types itself. So remember that we spent a long time in class talking about sedimentary environments and how a wind-blowing environment might sort out the silt-sized stuff. The smaller stuff might get moved off in one area as loess, and then it might leave behind all of the sand. You might have sand over here. So those two different resulting rocks even if they have the same porosity, are going to have very different permeability. Because as they start off, even without anything else, the actual pore throats, even without any water on them, the actual diameter of the pore throats is going to be much less. If you add water to that system, then suddenly a rock, even that has high porosity but has low permeability, and has high porosity but small grain size, and which is water wet, can functionally become impermeable. Okay, so let's talk about rocks. So first, a quick reminder what we mean by sedimentary rocks. Quick reminder here. So remember that these are forming as a result of weathering, and we've got chemical and physical weathering are our two subtypes of weathering. Let me get rid of this guy here. Our two subtypes of weathering are chemical and physical weathering. So chemical and physical. This is decomposition. This is just disintegration, just breaking it physically down into smaller pieces. And remember that they're interconnected. We talked about the way that these two things are interconnected. This increases total surface area for these processes to occur. So then we've got our material. We are going to erode it or remove it. Then we're going to transport it. We're going to take it somewhere. We're going to deposit it. We can do that by changing the energy in the system, so slowing down the flow, something like that. So then eventually we are going to, once we've got that sediment, we are going to transform that sediment into a rock. Transform it into, this is supposed to say the word rock. And how do we do that? Through three stages. 1, we bury it. 2, we compact it. And 3, we cement it. Collectively, those are the things we are doing in diagenesis, plus some other stuff that we don't really need to get into. And remember that we've got two classes of rocks. Our clastic ones are made of broken bits of stuff glued together, right? So things like a sandstone, and our chemical ones, right, are things like carbonates or evaporites like salt or gypsum. Those are the three big ones we're talking about in class: salt, gypsum, and our carbonates, which are our limestones and our dolostones. Dolostones I haven't talked about yet. I think you saw them in lab. Okay, let's erase these and move on to the next slide. So this is an example of this is a figure I pulled from a study of a particular reservoir rock that was relevant to petroleum, a place somewhere down in the States. I don't recall where it was. So this is a petrological and diagenetic study that you don't need to know those words that they did of the rocks to try to figure out what changes happened and when did they happen. And so I'm going to use this just to kind of show you the big categories of changes and when they kind of occur. So the first thing here, remember, is our compaction. So in compaction, we're taking our grains, I'll show you in a second, and we are arranging them in different ways, or we are breaking them to reduce porosity. We're making them closer and closer together. So that's the first stage. Kind of simultaneous, or actually even before sometimes the compaction, even near the surface, we can be altering grains, or we can actually be precipitating new minerals. So these are things that happen due to chemical, some of them biologically mediated reactions. So for example, the reactions of sulfite reducing archaea, right, near surface environments can produce sulfides, which then react with iron present around to produce things like this iron sulfide right here. So we can make, these are novel minerals that are formed near the surface. So we got novel mineral formation actually at the surface, or very, very shallowly buried. As we continue to bury more and more and more, eventually we start compacting. We get into this compaction stage here. As we continue through and keep burying and burying and burying, remember that the pressure is increasing and the temperature is increasing as we go along. That's a terrible arrow. Let me make a better arrow. The pressure and the temperature are both increasing as we move along. And so things start happening. And you'll see in a second, one of the important things that starts happening is we start both dissolving and reprecipitating certain minerals, and we can start forming, through chemical alteration, new minerals. So you get a whole series of things that happen here. These are chemical changes, right? Movement of material from one area to the other, and or actual changes of one mineral to another that take place as we start to heat this rock up. And so the end result is that what we started with as sediment and what we end up with at the phase over here where we actually start generating hydrocarbons, these are going to be two completely different things. This thing over here and what the rock is at the time we're actually making the hydrocarbon, these are not equal due to all of these diagenetic changes. We'll go through all of these guys very briefly now on. So first off, let's talk about two different kind of categories of porosity. So we can talk about primary porosity or original porosity, and we can talk about, there's our primary, we can talk about secondary porosity. So what do we mean by that? And you do not need to know every single one of these. I might put them in a multiple choice question, right? So you have some idea of these guys. So the big difference is that, so primary porosity was there when the rock was originally, or the sediment was originally deposited. So right now, if you get a bucket of sand and you are to pour water in, you know the water is going to disappear the moment you pour the water on top of the sand. Where's it going? Well, it's going to go in all this empty space. And I mean, a bucket of sand can literally be more empty space than it is actual sand. So it has tons of room for water to go into. On the other hand, let's say you get a block of cement and you start hitting it with a jackhammer. Well, you're going to make cracks in that cement. You're making cracks. This is actually, ignore that. We're actually down here. You're making cracks, right, in something that was completely solid. So it started off with no porosity and no permeability, but you're creating porosity in the form of cracks later on. And so this can happen to any rock. And that can be, it can happen absolutely to a sedimentary rock, but also it can happen to an igneous or metamorphic rock. So I told you before that igneous rocks, with the exception of ones that have primary porosity, like tuffs or sometimes vesicular basalts, right, that they are mostly useless to us. Well, that is the modifier to that statement is unless they have undergone brittle action and they have cracks in them. So you can get something like a granite, and if you put cracks in that granite, suddenly it is full of pore space. Absolutely. On the other hand, you can get something that had porosity, and you can increase the porosity, add additional porosity by putting cracks in it. So this works on both things that both had original porosity and things that didn't. It works on every kind of rock. Anything you put a crack in, you can store stuff in those cracks. So here's an example. There's my interparticle. So this is space in between the grains, but you can also have all of the background be solid, and you can have space within the matrix. So for example, if this was a snail shell, the snail shell itself is hollow. So even if you surrounded it with mud, so there was no space in between the grains of the mud, the inside of the clam shell or the inside of the snail shell is going to be hollow. So this is, again, mostly carbonate rocks, because we're talking mostly shell material, which is going to have the intraparticle. So all of the rest of these are solutional, right? These are all solutional. This one here, I'm actually going to go and smash things. This is just physical breakage. All the rest of these, I'm actually dissolving material away. So I'm taking stuff that was solid and I'm removing it, right, via dissolution or the transformation of one mineral to another mineral. And so these are all going to be secondary things over here. Right, so there's my dissolution specifically. Dolotomization we'll talk about. That's the transformation of one mineral to another. Here's the removal of H2O, of water from a mineral, which causes shrinking and contraction, etc. Okay, so let's move on. So a reminder really quickly before I move on. This is porosity that was there when the sediment was sediment. This is essentially going to be lost over time. It's going to get less over time. This is stuff that wasn't there originally, but we're going to add on later on by, say, breaking the mineral or dissolving the mineral. And so over time, as I bury the rock, this is actually going to get greater over this side, okay? So let us move on from there. So here are some examples in practice. You can see right here, let me get a smaller... I'll get a smaller eraser over here. So this is a rock that you can see. These used to be perfectly connected right here, but look, there's a crack right here now, and there's a crack right. There's a crack here. That crack's very obvious. It goes right through. You know, here's a crack right here that goes through. There's a crack that goes through. There's a little crack goes here. So this is all space now. The blue stuff here is the glue that they've put in when they prepared this slide. This is a microscopic image here. There's a I don't know, I think those are, I can't read that. But anyways, these are microscope images. And so you can see individual tiny cracks. So the glue invaded those cracks, but this could just as well be oil. And in fact, in this case, the blue is glue, but all this black stuff here is actual oil. So this is an example here. This is just a sandstone, and that space was always there. That's original porosity that was retained. This is one where, as you'll see in the process later on, it lost most of its porosity, and then it gained some secondary porosity. In this case, this is fracture. And then in this case here, these spaces that you see here, these spaces, those are the result of dissolution. This is a carbonate rock. Specifically, this is dolomite. And And you've got a couple of things going on. One, this kind of background porosity here is due to dolomitization. We'll talk about that later on, transformation of calcite to dolomite. And then the second part, these big spaces, those are dissolutional. Those are just the material literally dissolving and just leaving. It's going away because this material, remember, is quite easy to chemically weather. It's quite easy to dissolve. It goes straight into solution and just leaves. Okay. You don't need to know these terms here. I told you there are multiple conflicting classification schemes for limestones. I just care that you know that different kinds of limestones exist. Like a chalk is different than this thing here full of big pieces of shell. I want you to understand that difference, that they exist in practice. But beyond what you learned in lab, which was, you learned the difference between limestone, fossiliferous limestone, coquina. You learned what ooids are. Right? These things here are probably ooids over here. They might be little fossils. I'm not really sure. I can't tell at this scale. So these are one classification scheme, and you can see, so a mudstone in this case, they are using, confusingly, the term we used for shales. They're using it for a very fine-grained, right? So it says mud supported. The mud here, they just mean what size the material is. But the mud is going to be tiny fragments of calcium carbonate, mostly. Some clay, too. Or you could have, you can see this is matrix supported here. So this is matrix supported, and you've got some shells in behind. That would be a wacky stone or a wax stone, a pack stone. The shells or the clasts here are going to support themselves. So this is, skeletal support over here, or grain supported. That's a pack stone. So I'm honestly not super concerned that you know. In fact, you just don't need to know these things at all. But I do want you to see that there can be very different textures and very different degrees of primary porosity and permeability in limestone. It's like this rock here is very different than that mudstone. This thing's going to be functionally impermeable unless after the fact I put some cracks in it. If I put some, I put cracks all the way through here afterwards, sure, now I've got permeability. But if I don't do that, right, before I do that, I have zero permeability. On the other hand, this thing potentially has permeability, although note that all of this space in between seems to be mostly occupied by mud. So the actual permeability to start off with is probably very low because this is very poorly sorted. These are all terms from class, remember, from lab. This is very poorly sorted. And so really this is going to be super low. This is going to be super low original porosity as well. This looks like it's a bit higher over here. All right, again, you don't have to memorize this. I just want you to see, here are those same terms. There's your vuggy wax stone, your grain stones, etc. I want to note that with carbonate rocks, and the same is true for different reasons largely, in clastic rocks, both the permeability and the porosity can change over time. And they can change either by decreasing, by getting less, like this over here, they can get less, or they can get higher, right? Higher porosity or higher permeability. And they can do that by things like, cracking. This guy here is supposed to represent fractures right there. That's fractures, right? This guy over here is leaching. So that's dissolution. Where's my leaching? Here's this, it's going to dissolve. On the other hand, and we'll talk about this in a second, this thing over here is compaction and cementation. So that's going to decrease your permeability. So the permeability and porosity are going to change, right? They can increase, they can decrease, depending on the particular starting mineralogy, the particular starting characteristics of the rock, and the particular geological story, right? What happened to it during its burial? How long, what conditions were they exposed to, etc. You need to know all of that. It's not simply enough to say, I have a wax stone. I want to know what happened to it afterwards, right? Was it heavily dissolved, or was it fractured, right? Or in fact, did it get so well cemented that now it has, no porosity and permeability at all? So I need to know its full geological story. This is a really complicated diagram. It's not complicated, it's just kind of obnoxious to read, but essentially what they're trying to show you here. So here is porosity, here is permeability on the y-axis over here. So with these guys here, this is degree of sorting going this direction, and this is grain size going this direction. So let's say at this spot right here, that is a coarse-grained, very well-sorted rock. And so you can see it has really high permeability. And note this is a millidarcies, and this is a log scale over here, and this is percent over here. And so a coarse-grained, very well-sorted rock, right, is going to have excellent permeability and excellent porosity. Okay, a very fine-grained, very well-sorted rock. Remember, we already talked about that coarse and the very fine-grained one. They're actually going to have the same porosity, but the permeability is going to be much lower. In this case, they're saying it's almost 2 orders of magnitude lower, right, than the coarse-grained one. And that's because, remember, in very fine-grained ones, the actual gap between the neck of those 2 grains, I might as well make those actually be grains, that gap is going to be much smaller. So it's going to be harder for hydrocarbons to wiggle through, especially large molecules, and especially if you've got a coating of, say, a coating of water around the edge of this, which is going to make that incredibly narrow for anything to go cruising on through. So as a general rule, the coarser the material, the greater the permeability, and the better the sorting, the greater the permeability, and the greater the porosity. So as you change permeability and as you change porosity, generally speaking, as you change sorting and as you change grain size, as a general rule, both of the permeability and porosity are going to decrease. But in particular, the degree of sorting. And remember, the degree of sorting is just talking about the difference between sizes. So if you've got a bunch of little things and a bunch of big things, the little things will fall in the spaces and they will block the pathway. Right? So you actually have less functional porosity, but you also have less permeability. Okay. Yeah, well, you have less porosity mostly. Permeability is dropping as well, as you can see, but permeability is really largely affected by grain size because it's going to make the pore necks be smaller to start off with. So you have a suite of changes. So we've got these various original differences in porosity and permeability, but of course they're also going to change dramatically as we start to bury the rock. Now I already gave you some examples of that with carbonates to show you what that might be like, but let's just look in more detail at how and when these changes can take place. So first off, let's be in the near surface. As a reminder, let's actually just quickly go back up to this diagram I had, which was, where was the diagram? Right here. So remember, we've got these various stages. So early stages where we've got these changes in mineralogy, new minerals growing. Then we're going to compact, and then we're going to start cooking and squishing and causing various chemical changes later on. All of that's happening long before we actually generate our hydrocarbons. Let's go back on down to our diagram, which is right here. Okay, so the earliest stuff that is going to happen, here is our sediment. Let's get a thing here. Here's our sediment. So say our river is coming in, it's bringing our sediment in, so it's coming in and it's being deposited here. So we got layers of sediment building up, and of course they're going to get finer as you move out. This maybe is a buildup over here, okay? So we've got that sediment going on here. That sediment is now interacting, right? It's interacting with the seawater around it. When you bury it thick enough, it can actually interact with rain over here. When he says meteoric waters, that just means rainwater and surface waters. And of course, these things are going to be a lot more reactive than the waters over here. Don't have as much stuff dissolved in them, so they're more likely to take material up, but they also tend to be quite acidic because you've got carbonic acid from here and also from interacting with cellular respiration in that and materials in the subsurface. So you're going on both biological and abiotic stuff in here. Anyway, so these meteoric waters can be very reactive, and they're interacting with stuff here potentially, plus on the surface it might be interacting with, if this is marine, with the seawater. You've got organisms living in the sediment itself, and they're doing things like sulfur-reducing bacteria that are sulfate-reducing bacteria. They're taking that sulfate and they're making sulfides out of it, which are reacting and producing things like pyrites. All of that stuff's going on here. So what's happening here? Well, the first thing that's going to happen is this reaction with this meteoric waters can cause chemical weathering. And one of the chemical weatherings we talked about, remember, was the transformation of things like feldspar and biotite and muscovite into clays. And this is a type of clay there. So we talked about that. We actually use as an example for our chemical weathering early on. And then we've got little shells of things in here. These are little organisms. They're falling down. And so we can actually be adding more carbonate and silica into the system in the form of tiny little microscopic shells coming over here of the organisms that were in the water column here. And finally, this is the precipitation of authigenic. That just means growing in place. Geology has lots of fancy words like this. So these are the examples of things like chlorite and pyrite that are actually growing in the sediment when it's at its near surface. So all of this is happening while it's just essentially on its surface. If you are in a carbonate-rich environment, you can also actively be cementing, that is, growing crystals of carbonate in between the pores, right, in between the individual grains, which glue them together. So in a really carbonate-rich environment, you can actually have that cementation taking place right at the surface. But usually it happens at the further into the subsurface. So let's look at these guys in practice now. So here is an example right here. That space right there used to be a feldspar crystal. So think about the sands we looked at. Remember the term for a feldspar-rich sand? That was going to be an arkose or arkosic sand. So this, if this has lots of feldspar, it might be an arkose. Well, once we have this in an environment where it's interacting with, acidic waters, it can break down, right? And it can transform into something else. So we've changed that feldspar. And what have we made with it? All these little clays over here. See these tiny little clays? So you're going to say, Jason, that's increased porosity. Well, I mean, it kind of has, except it's transferred that material over here. It's just moved position more or less. But really importantly, you see how small and compact these things are? These things filling up all this space in here. This is what they look like under a really high power microscope. And you can see that we may have increased, maybe we even increased overall porosity. Probably we've just shifted around, but we have significantly decreased permeability, because before you used to be able to flow through this space in between. Now this space is all filled in with stuff. So here is the alteration of feldspars through to kaolinite, through to a clay mineral in the near surface. So here is another example of what can be happening. So here we have our sand. When we get our sand, and we start off with our sand, that sand can have really high levels of porosity and really high levels of permeability. So like tens of darcies as opposed to going down to millidarcies, right? This is dropping down to a quarter of what we had before. This is a microscope image of what a sandstone looks like, and you can see there's very little space in between these things. So what kind of changes have happened as we've gone along here? So now we'll talk about those changes. So you can have the stuff that's taking place at the surface. You could potentially be even cementing a little bit. You're creating authigenic minerals, remember, growing them in place. You're dissolving feldspars and growing clays. That's happening here. It's happening right here maybe. But as we start to take it and bury it deeper, 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 deeper down, that is, as we put more material on top of it, which forces everything to respond by kind of sinking down, all of the weight of that overlying material is going to crush the rocks below. And the first thing that's going to do is it's going to force them into more preferential alignment. So the analogy I always use in class, and this is an important analogy for your own lives, is when you go to the movie theater, you know that a bucket of popcorn costs like $7. It's ridiculous. So I'm not going to lie, I'm a little bit cheap when it comes to this. So every time I get my popcorn, and I feel like a jerk doing this, but I do it anyways, I get my popcorn, and I take that popcorn, here's my bucket of popcorn, and it's got, all the kernels up like this, and I just whack it up and down. I tap it on the surface, and all these kernels are going to drop down in. And that's not because they're actually breaking. It's because they're changing their arrangement. They're changing their arrangement, and that's going to decrease the amount of that space in the bag, which is occupied by air rather than popcorn. That's going to allow more space for popcorn. So I whack it down a few times, I change the arrangement of the popcorn, and then I give it back, and I say, hey, can you please top this up? And they look at me like I'm a cheap person. They say, aren't you a professor? Don't you make big money? And I say, you should see my paycheck. It's not as good as you think. You should be an engineer. Don't be an engineering instructor. Anyways, that's the first thing. This is just the arrangement. We're just compacting. This is the popcorn thing. On the other hand, if I just started actually physically squishing the popcorn, just grabbed it and jumped on top of it, then I'm actually going to break the kernels of popcorn themselves. So that's the second thing here, is I'm actually physically breaking it. That's actually... this is not actually what they're showing there in that diagram. Ignore that. They're physically breaking it. So let's see these guys in practice. So moving along here, Here's my first thing. This is perfect arrangement. Imagine you have perfect spheres, and those spheres are arranged in a perfect cubic way. Half of this space is going to be porosity. So this is what the movie theater wants your popcorn to be like. Jostle around a little bit, and you just change the orientation of these things relative to each other. And now I've decreased my pore space almost by half just by doing that. So jostle your popcorn, but also as the rocks themselves get pressure put on top of them, or as the sediment itself gets pressure put on top, it's going to force these things to move around into a more compact relationship. And that's going to substantially change porosity. So this is just packing. So if I asked you about compaction, about porosity due to compaction, you're going to say, 1, changes in packing arrangement, and 2, the other part of it is actual breakage of it. So if you put enough pressure on it, where one grain is hitting another grain, they will actually fracture. So that could, in some degree, increase. You're getting this tiny increase here in porosity, sure, but also simultaneously, they're now fitting much closer together. So this little tiny, let's say you make a little crack there. If you take this whole grain and make it fill in that spot there because it's moved into this place, this little tiny bit of increased porosity from that crack is not going to offset the loss from changing in arrangement. So as you smash these into smaller and smaller pieces, it allows them to move into the spaces and fill them up. So you're essentially decreasing sorting, right, by actually making smaller pieces. So I'm going to note that here is some actual experimental data, and you can see that the greater the stress, this is the more pressure, the greater the loss of porosity overall. Okay, that makes sense, right? But notice that this is the starting diameter. So this one here started at almost a millimeter. This is a sandstone. This started really fine. And you notice they're both losing porosity as you crush them. But also notice that this one, the coarse one, is losing porosity a lot faster. And why is that the case? Because where you started off with one big crystal, one big thing like this, and one like this, right? They're just touching on this little spot right here. And that means that all that pressure is going to be concentrated there, so it's more likely to break. Where you've got a bunch of little things, more of their surface area is going to be in contact. So it's really much harder to break these little guys than it is to break this big guy over here. So you're going to get a change, but the change is not going to be equal in all rocks. So a very coarse-grained sandstone is actually going to compact more due to physical breakage, fracturing of grains, than a finer sandstone or a siltstone. At the same time, if we go back to this previous slide here, at the same time, if we have one which is, poorly sorted, so it already starts off, and these are already filled in, all these spaces by smaller rocks, then there's less I can do by moving these things around to gain a change in porosity. So a well-sorted sandstone will actually have more potential to lose porosity over time than a poorly sorted one, even though a poorly sorted one is going to start off with less porosity to start with. So the change will be different. Well, the change will be different in those two examples. Okay, what else do we have? So here is a term that you had in lab, immature versus mature. What do we mean by immature? Immature, we're talking about less quartz relative to easy to dissolve or destroy minerals. So that's chemical or compositional maturity. We also mean degree of sorting, right? Low sorting equals immature, high sorting equals mature. We're talking about grain size on average, right? We're talking about grain shape on average, etc. So all of these things are going to change porosity now, or change response to porosity. Now, overall, mature sandstones are going to retain their porosity to greater depth. And you're going to say, well, wait a second, Jason, you just told me that a very well-sorted sandstone could potentially lose more porosity because it starts with more porosity. Yeah, that's true. But on average, when you take everything together, largely because of the fact that a very mature thing has got lots of quartz in it, and that quartz is going to be very both mechanically resistant to breakage, and also it's going to start chemically dissolving later on as we go along. Ignore that second component, actually. It's going to be mechanically different to... The other thing that's involved is that an immature one is going to have lots of lithic fragments, it's going to have lots of feldspar, and those things easily dissolve. Okay, here it is. Here's again some actual real-world data. Over here we've got porosity. Over here we've got burial depth. These are volcanic sands. These are arkose, remember feldspar rich, and these are quartz arenite, which means, remember, quartz with very little mud in between. And what you should see is that the quartz rock retains its porosity to greater depths. This is 4K, right? So they're all losing porosity as you bury them. This is a very immature one. This is just be made of basalt, fragments of basalt. So these things break down very easily. The arkose stuff, it's physically less strong, but also remember this is chemically more reactive than this stuff down here. So there's an example of how in the real world, this is actual data, right? More mature rocks have greater stability over time. All right, here is one more idea, and this is actually probably the last real idea that I want you to think about today. Next class, we will move on to carbonate rocks for a little bit because this is getting a little bit long at this lecture already. So that's this idea of pressure solution. So what do we mean by pressure solution? Well, pressure solution is what happens when we put sufficient pressure on two grains at their point of contact where they actually go into solution. And that's what's happening at this line right here. So we are compacting, we're continuing to compact the rocks as we go down this whole way. But at this point here, which is around about 100 degrees C, we are going to transition from mostly being mechanical compaction to being chemical compaction. So at this point, remember, we're rearranging, we're breaking minerals. That's how we're gaining, or we're losing rather, that's how we're losing porosity. Down here, we're losing porosity because we start actually dissolving away, right? And changing the shapes as a result of dissolving away minerals. So let me show you what that looks like. So over here is a diagram kind of illustrating this. And let me get a bigger, I'll get a bigger thing here. So here is the point of contact. That's where all the pressure is, right? And more angular they are. So at this point, that's the only point that's in contact, which means that this is where all the pressure from all of that overburden is manifesting. So this material goes into solution. And when it goes into solution, it's not going to just leave the system. It's not just cruising out like this. It's going to migrate just over to the low pressure area, and then it's going to reattach itself right there. And so the end effect means we're taking this material right here and moving it over here, which is ultimately going to build up stuff here, remove stuff right here, which means these guys are going to start stitching themselves together until eventually they have enough surface area and contact that at this current pressure they kind of stabilize. So this is pressure solution. So literally forcing material into solution and causing it to migrate over and then come out of solution in an area that is under less pressure. So it's going to do two things. One is these rocks are now going to sit closer together because they used to be sitting up on these little points here, and now they're sitting in contact. So this whole thing occupies, less volume. I've just lost volume over here. But the second thing is that as this stuff migrates over and reattaches itself here, it can glue them together. So they're becoming seized together and glued like this. So that is part of what is cementing them together. And in this case, by cementing, I literally just mean gluing them together. So I've taken my sediment and I've transformed that sediment now increasingly into a rock. So I'm making this increasingly into a rock. And here it is actually showing it in real world. So this is the original grain. You can see it's all beaten up under the electron microscope. This was a grain of sand. You see this perfect crystal over here? That's not what you'd find in nature if you ever look at a grain of sand. That's new stuff. So what's happened is this has migrated out of a point of contact, come out over here, and it has grown on top of this existing crystal lattice here. And it's growing new material over top here. So this is our quartz cement. You can see that this cement, these are interlocking together. They're attached together. So now these two grains, which you could have picked up and moved apart, they're now actually glued together by this new material. So they've been cemented. So that's taken our sediment and it's made a rock out of it. Okay, so how is that going to affect porosity? Well, obviously, and permeability. Obviously, you get the loss of volume as you start to compact it. But you're not actually removing material, remember. Remember, you're not removing material. You're not taking it out of the system entirely. This material doesn't move out of the system, right? It doesn't exit the system. It doesn't leave. Instead, it just moves. So you end up getting material that was, it was quite porous, and I'm losing that porosity by cementing it together and by making these guys in close contact. I've also reduced permeability. I used to be able to cruise straight through here. Now I've got cement in there, And so I cannot move in between there. So I'm going to lose both porosity and now I can't cruise through here, right? I'm blocked here. I've also lost permeability. So once I hit below about that 100 degrees C-ish temperature, I'm going to start going through that process. And that process will continue on until either I completely fuse the rocks together, I've lost all porosity, all permeability, or I move back up and out of that range where things become chemically unstable. Now another thing can happen, which is that if I either put oil in the system, so if oil is filling all this stuff in, stopping the migration of silica in solution, right? Silica is just what makes up quartz, or if I grow a layer of some other mineral over top that acts as a shield, it will actually stop this material from dissolving out and moving in. So either by growing a thin crust of some other mineral that's more stable at those pressure temperature conditions, or by filling that void with oil, I can actually stop chemical compaction. But otherwise, as long as you stay down within this range, as long as you're buried deep enough, you're going to continually lose porosity. So now when we think about the thermal history of a rock, remember in our previous talk, we were talking about how the thermal history of a rock in an area, you want to know when was it buried? I also want to know how long was it at a particular depth for before potentially the emplacement of my hydrocarbons. Because if I keep it down at too hot a temperature, if I keep it down at this, this zone here, eventually I get to the point where I filled in all this material and there's no room for hydrocarbons to go. On the other hand, if I put hydrocarbons in there before I finished off the complete loss of porosity through pressure solution and cementation, then the hydrocarbons themselves are going to block new material from growing in there, just like they are over here. So one more thing that I want to show you, which is just this in practice. This is ultimately where you're going to go. So this is a quartzite. A quartzite is a metamorphic rock and it's useless to us. If you want to see one in lab, come on down and I will put a drop of water on it and you'll see it'll just sit there. Put a drop of water, it just sits there. It cannot go into this rock because this rock is completely poreless. And this is what they look like in thin section. You can see every single surface. These black, white, gray, these are all the same mineral. Remember, this is just how they look depending on the angle that you have them relative to the light. But these are all quartz, and every one is perfectly interlocked. This has zero porosity at this point. This might have been a beautiful sandstone, but I've cooked it for too long and at too high temperatures and pressures, and it's lost all of its porosity. So that is why we need just the right conditions as well if we're trying to build. You need the right thing to start off with, say a nice sandstone, but it needs to have the right burial story as well. Otherwise you end up with a rock that is no good for acting as a reservoir or as a pathway for oil to flow through. So the final diagram I want to show you before we end off this lecture is this one right here. So here is the zone in which we're getting chemical compaction occurring, specifically around kind of 100 degrees centigrade, right? Mechanical compaction is taking place up here. This has it around 75. We're going to use about 100 for our point at which it's happening. So mechanical compaction, we are jostling them around, changing orientation, cracking the grains as it goes on. Then I get to the point where I start to actually cement it together. At that point, I'm no longer going to be actually breaking anything anymore because it's now glued. And I'm not moving them anymore because they're glued. But I'm continuing to lose porosity and permeability because I'm now dissolving material and re-cementing it around. Now note, let's imagine a burial history where the rock is getting buried deeper, deeper, deeper. Now it's to the point where it's losing and losing and losing. But then imagine that over time, that rock starts to come back up to the surface. Well, how does it come back up to the surface? Well, remember, we already talked about this where if you build a mountain, the pressure of that mountain is going to deform and force the bottom to go down deep. But then if we start eroding the top of this mountain, we start cutting off the top of this mountain, it's going to pop back up. So if we're just talking about this thing at depth, as we erode the material on top, that point X is going to start rising closer to the surface as it rebounds, right, isostatically. Remember isostasy, right, as we remove the material at the top. But both in the journey down and in the journey back up, it's going to continue losing porosity and permeability until eventually it gets out of here. And that's the point where it becomes chemically stable again. You've got some other stuff over here we'll talk about, which is the illitization of kaolinite. We'll talk about that next class. But that right there is essentially where I want to leave you. And I'll show you that on this next slide right here, we have kind of a summarization thing that talks about all of this stuff together. So next class, we'll move on quickly to carbonate reservoirs and carbonate rocks and how they're affected by burial. And then we'll talk some more just about actual properties of the reservoirs, and specifically how original things like ripples or cross bedding, right, or the lateral changes as you move from the channel of a river to the floodplains beyond, how those things can affect the interconnectivity of reservoirs, and therefore how they affect it from an engineering perspective and from a total, hydrocarbon storage potential perspective. So if you have any questions, please let me know. Otherwise, please go and do the quiz right now.